Now suppose that this graph represents the thermal energy added to a mass m of a substance in order to change the temperature. Okay, this is the thermal energy that actually goes into the substance, goes into the random kinetic energy of the molecules, or actually it's not so random if you have a crystalline solid or something, but it goes into the kinetic energy of the molecules, or the kinetic and potential energy of the molecules, depending on the situation. Now, over a large range of temperature, the rate at which you have to add thermal energy might change with temperature. Okay, the rate at which thermal energy with respect to temperature is added with respect to temperature, or the amount of thermal energy added per unit of temperature, might change, and that's going to change the slope of this graph. The specific heat, which we're going to call C, which is the amount of energy you have to add per unit mass and so forth, a concept you're familiar with, is defined for a small temperature range, approximately defined by the equation delta Q equals mc delta T. That is, you multiply C times delta T and then multiply that by the mass, you find out how much thermal energy is required. And this is a concept we're real familiar with. Calculus of this is, in the limit, we take the, or we have a differential definition. The rate at which energy is added is mc times the rate at which temperature increases. And we define C then to be 1 over m times dq over dt, and this is something that's defined at every point of this curve. Often we treat C as if it's constant, and then what we're saying is, well, over the part of the curve, the Q versus T curve that we're looking at, the dq over dt doesn't change by much. That is, the slope of this graph remains relatively constant. If we have thermal energy passing through a substance, like on a cold day, thermal energy passes from the inside wall to the outside of that wall in your house and gets transferred from inside to outside, which is something, of course, you insulate your house to reduce. Okay? We're going to define H, the rate of thermal energy flow, H for heat. I tend to use the term thermal energy and not use the term heat very much, because we want to remind ourselves that this is energy that we're talking about. But the thermal energy flow is defined as the rate at which energy flows, derivative of Q, the thermal energy, with respect to T. Now, in the case, let's say, of a wall, we can think of the fact that the rate at which thermal energy passes through the wall is going to depend on three things. One, obviously, is the area of the wall. If we've got twice as much area, we expect to have twice as much thermal energy flow, all other things being equal, inside and outside temperature, thickness of the wall, and so forth. If the area increases, we expect the thermal energy flow to increase by the same proportion. L stands for the thickness of the wall, and that's something that's going to reduce dq dt if it increases. Okay, if L gets larger, that means the wall gets thicker. You're going to have a smaller temperature gradient, and you're going to have less thermal energy flow. The TH minus TC is the temperature at the hot side minus the temperature at the cold side of the wall. And that's the temperature of the wall at the hot and cold side, not necessarily the temperature of the room and the outdoors. That's your difference in temperature, which might be represented by a delta T. And of course, this could be then a delta T over L, which is what we mean by temperature gradient. So we're going to say the thermal energy flow is the coefficient of thermal conductivity, K, which is a constant, times the area times your temperature gradient. And it's really your temperature gradient that drives the thermal flow for a given substance. K is a property of a substance. We can generalize this definition, and really, I used a differential notation up here, dq dt. I should have used a delta Q over delta T, perhaps, but let's just say this is approximately equal to this. We can generalize to a situation where the temperature gradient might not always be constant as it is in a wall. For example, imagine that thermal energy is flowing through a rod or a bar. You're going to have a cross-sectional area A, and you're going to have a temperature gradient at any point of the bar. If the bar gets narrower at some point and fatter at another point, this temperature gradient might not be constant, in which case you would express it as a dt over dx, something that might be a function of x. And we simply take the limit of the delta t over L and call that a dt over x. So that the rate of thermal energy flow is constant here, times the area, times the temperature gradient. And the temperature gradient is defined in differential terms. We also say that this is A delta T over R, where R is regarded as thermal resistance. Now the way we think of this, if you got a wall of area A in a temperature differential or a temperature difference delta T, then a larger A and a larger delta T tends to make more thermal energy flow through the wall. A large resistance will tend to make the thermal energy flow more slowly through the wall, and it's the R value or the resistance that we want to increase in our walls. Now, comparing this equation with, let's say, this original definition up here, we can see that R has to equal L over K. And that's an easy comparison. Make sure you understand that.